This is some basics on the associate command. As always, I suggest going up here and making a new markdown file. So we're going to go in and go to new file and go to a markdown. We can call this associate practice. So let's just do this and call it the first association practice. So this will create a markdown file for us, and we can knit it any which way we want, but it's just a good way to practice. You can fill this in for yourself and even give it to your friends. So it actually comes with the R chunks already in here, and something a lot of people don't know is that you can add in your own R chunks. So we don't need all of this word processing between here. Let's go ahead and just add a new R chunk in by going right here and going to insert chunk. So there you go. New R chunks added in, and let's start using them. First thing we want to do is load in a data set, but we also want to load in our library. So let's load in reg class that we use for this class, and we've loaded in reg class. Now let's go ahead and look at some of the data in reg class. I'm going to go here and use the data set survey 10, one of my favorites. And I always suggest using the autocompletes because it'll help you not make mistakes. If I see something come up, I usually want to click on it because it'll put it in quotes when it needs to be in quotes, and it'll do everything proper, quickest and best way of doing stuff. So as you'll notice, the data set has now been loaded in. So first I had to load library reg class because survey 10 is inside of this. Just to make sure everyone knows, this is the first video, so we can scroll down here and we can go to packages and take a look for reg class, MNOPQR. It's in the second set. And here is our reg class right here. So reg class, you can see, has a lot of different packages in it. If you go all the way down to, it doesn't have packages in it, it has a bunch of data and it has a bunch of functions and everything, and you can see everything here. So you could get even more detail on this right here, just all the variables in it. And let's take a look at all the variables inside of this. We have the names command, just to run survey right here, survey 10 on it. And running this, and I'm using control enter, or you could use command enter to run it. This just gives me the names of all the columns doing names. Lots of other things we can do. We can check the dimensions of it. And as we see, it's 699 with 20 variables. It means there's 699 rows and 20 variables. Lots of good stuff here. But let's start talking about the associate command now that we have the data loaded in. We have the data loaded in, and in our next chunk, we're going to run an associate command. Let's start with some categorical relationships here. So we need two categorical variables. So let's go ahead and do associate, which we need the reg class function on. And let's see here. We need two variables that are categorical. Gender, and also we have handedness. Handedness is categorical. So it's a categorical relationship. Let's see if we can predict someone's gender, because that's the Y, by their handedness. If you notice, I have here the format of Y tilde X. This is my Y variable, this is my X variable. But it does not know where these are until I tell it where the data's at. So the reason we do data equals is because gender and handedness are inside of this data frame. Now if I had gender and handedness just out here in the open, it would work. But since they're inside the data frame, I have to call the data frame afterwards. The associate command can handle a lot. Make sure you're getting the right output. This is so key because if you put in categorical variables, you will get, as long as my plot over there is big enough, you will get a mosaic plot. So you know you've done categorical variables if you get a mosaic plot. So here's our mosaic plot. Let me rerun it. Sometimes it'll shape a little bit better in there. Let's go to the zoom to get everything nice and neat. There we go. And you notice here we have people who have the ambidextrous who are kind of making the plot look a little bit messy. Try and make everything look as nice as we can. And I think that's ambidextrous, and that's left. I'm going to use a different plot here since I don't like the way that one looks. Let's go over to survey 11 data and get the names on it and dimensions for the heck of it. You can also use Control-Alt-C, I believe, to run the whole chunk. I do not know the quick command on Mac, but you can just select it all or choose to run the chunk when you have the commands over to the side. So now I've switched up my data frame. And let's see if we can get something that looks a little bit nicer in here. The names is the important part here because we need to get two categorical variables. So let's go ahead and take a look here. So let's see. Hair color. That's good. And born in Tennessee. That's from some pretty easy ones. So let's see if we can predict whether somebody was born in Tennessee from their hair color. And actually, I'm going to switch these because we'll keep it the way it is. We can do it either way, but this is hair color explaining if someone's born in Tennessee. I feel like we're going to have... Oh, this one didn't come out so bad. With the zoom, it's going to look a little bit better. There we go. This is what I want to see here. Wow, holy mackerel. I'm shocked to see this because we have to know what we're looking at here in this output. What we're looking at here is a mosaic plot. Since I said hair color was the x variable, it goes on the x-axis. And don't get confused by these x's. That's just a variable we took in this data frame. It's just called hair color. This is called born in Tennessee. It's called x10.born in Tennessee. It has nothing to do with it being on the x or y axis. So with this in mind, we see that there are a lot of students who are not born in Tennessee with black hair. And when we get down to the plot right here, this is the important one a lot of people don't know how to interpret. And this goes to where you really need to read up on the book on how to interpret this. Because what we have here is a discrepancy histogram. This is a univariate view of what would happen if we mixed up all of these right here and then randomly assigned people to being born in Tennessee or not being born in Tennessee. And the most likely thing we would see is that there'd be no relationship. Why would one group all of a sudden have more of the born in Tennessee or not born in Tennessee? And then we calculate the discrepancy for that. And we do that, in this instance, 500 times. So you see, all of these are different permutations where the discrepancy was calculated. We have 500 different permutations here, and that's what's filling up these bins. So this one has a lot, this one has very few. We didn't get many very high discrepancies up here. But then we look at ours. Ours is not in this bin right here. Ours is a unique one that we're saying, well, what could happen by chance? Could ours happen by chance? And if you notice, there's not many above ours. There's like 2 here and 2 here, so that's like 4. 4 out of 500 is a very small amount. So when you look at 4 out of 500, and that's the p-value right there, we're looking at 4 out of 500 right here actually, and just to show everyone, if we do 4 divided by 500, that's it right there. That is literally how the p-value is being calculated, is 4 out of 500 is going to give us a p-value of 0.0008. And I really like this one. Great example we got here, because there's 2 observations in this bin, and there's 1, 2 here. It's hard to tell if our observation is higher than these, because anything between here and here would be in this bin. So it could have been 3, could have technically only been these 2 that were above ours, because if there were observations right in here, then they would go into that bin, but they would not be higher than ours. This is how histograms are built due to the bin size. And it just so happens that those 2 observations are above ours. They are on this side of the bin. And then these 2 are definitely above ours. So the p-value, as far as I could estimate, was somewhere between 0.0004 and 0.0008. And now we get to our confidence interval. And this is a key part of the interpretation, because randomness might produce different results. And because of that, we need to give a confidence interval, because what if the simulation turned out a little bit different? And so we kind of give it some wiggle room, because with the amount of permutations we have, we would say we're 95% confident that the p-value for this test is contained in the interval 0.002 to 0.02. And this is a good thing. This means we have confidence that this test is significant, because I'm pretty confident the p-value is below 0.05. So this test does look to be good, but I'm going to do something bad here. Let's put in permutations equals 50. And now you notice the bins are a lot more sharper and there's fewer bins. It's because there's only 50 permutations going into here. Our graphic up here did not change because we still have the same results that we got. Now, as you'll notice, there are no results above mine, so that gives a p-value of 0. That's why the p-value is 0, because the probability of my results or results more extreme happening due to random chance, these are random chance, is actually 0. It doesn't happen. But here's the interesting thing. Since we have so few permutations, our confidence interval is now wider, and we would say it is inconclusive. If this is on the test, I hope no one misses it, because we would say that although we have a significant p-value, we are not confident it is significant, and thus it is inconclusive. What do we do to fix that? increase the permutations. And as you notice, this time I'm doing it with a lot more. By default, it's 500. This time I'm doing 5,000. Last time our interval was between 0.002 and 0.02. This time our interval is between 0.0002 and 0.0006. And there's actually more. It made the bins wider this time. That's why they don't look to be as sharp. And we get what is a very good chi-squared distribution. You don't really need to know that, but this is a chi-squared with 3 degrees of freedom. 1, 2, 3, because it's a 2x4. Stat 201 stuff right there. But the discrepancy statistic and how it's calculated is important, that we look at our discrepancy and then we simulate results to find out what's the probability of discrepancies like ours or more extreme. And that's the whole key to the p-value. Our discrepancy was 13.182122. You notice that does not change no matter how many times I change the permutations, because we will still have the same discrepancy. It's just that in our simulated results, we might see that discrepancy or discrepancies more extreme a different amount of times. But you notice the results come out very, very, very similar. I'm getting p-values all around 0.0004, 0.0002, and that's because that does look to be what the p-value is. Confidence intervals even suggest that. So we have something here that is very statistically significant. Does it have practical usage? Maybe. What we do see is the group that has the difference is the students with black hair. Why that is, who knows? This is somewhat of a difference. I wouldn't know how to use it. But let's try one more here. Let's look at what else we have. So, saw the last Harry Potter. Yes, let's use that one, and let's do gender. So let's see if seeing the last Harry Potter, this is, you can tell it was a while ago, because now we've got Fantastic Beasts and Where to Find Them coming out. And let's use gender. Easiest thing to do is to copy paste, and this is how you should quiz yourself, is you should try doing these results. So we're going to predict someone's gender, that's our Y we want to understand, using the X if they saw the last Harry Potter. And once again, these are just variable names, X has nothing to do with it. Y tilde X, data equals, and then I'm changing the permutations. So here we are, we get the results, and oh, wow! Everyone was seeing the last Harry Potter. These results are not significant, and we're confident of that because our interval does not contain 0.05. You would think, so if they saw the last Harry Potter, yes, it is a little bit more female. And that's not significant. We do not have significant results right here. The discrepancy value is not that high. It could happen by random chance. We see that in our results. Well, I'll be. What else? Have you spent a night in jail? I'm always going for things I think might have some sort of relationship. Let's see if you've spent a night in jail can explain someone's gender. And what do we get? So the people who have spent a night in jail are overwhelmed. This is a good one. The people who have spent a night in jail are overwhelmingly male. And, you know, we never try to assume things about the world, but if someone's like, oh, my friend spent a night in jail last night, probably a guy, but it could be a girl. And so we can actually go up here to some of the values now to take a look. And what we should read here is that given someone has spent a night in jail, this is how you read this right here. Given someone has spent a night in jail, the probability of them being female from this is 3.2%. The probability of them being male is 96.77%. So that's what you're seeing there is that little tiny bit of black is the females who have spent a night in jail, and this red right here are the males who have spent a night in jail. Now, most importantly, what we have here is a very significant relationship, and you can note this because there's a large discrepancy between the blocks. You'll notice from here to here, you see this big jump, and you often get big discrepancies. That is the discrepancy. If the blocks are flat, there's no discrepancy. And we see, given someone has not spent a night in jail, the probability of being male or female. And it doesn't matter that they're relatively equal because we could have more males or females in the survey. What matters is the difference when we go from the different values of X, because you notice this is on our X variable, and how it differs from the marginal. The marginal is just for all everything in our survey. So this is the probability of being male or female in our survey. And we do have more females in the survey, and someone could say, well, there's more females in the survey. And you say, well, the X variable radically changes the Y, and that's the important. We see different levels of Y right here. for the x variables. When we change our x variable, we see different levels of the y. If you've broken a bone, we could take a look at that one real quick. Can that explain gender? Maybe, maybe not. We did this in Stat 2-1 for them too. And yes, it does. You see the people who have broken a bone are more likely to be male. And this one is not as big of a discrepancy. You can compare discrepancy values. Since these are both 2x2s, the discrepancies are comparable. And you'll notice for the previous one, you see a bigger discrepancy. And the discrepancy value for the previous one was 32.6 right there. And this is how we understand the output from association for categorical data. And there's a little more up top, so let's talk about that just in brief right here. Expected counts and our counts. So let me increase this window size right here. What we have here is our expected counts. Let's go back up to it. Our expected counts and our counts. These are the actual amounts right here. 232 females said no, and 151 males said no. Here's the expecteds. We should know how to calculate expecteds with row total times column total over grand total being the formula. So if you were to take, let's see right here, 343 times 383, and then divide that by 628, we should get 209.2. And there it is, 209.2. If you notice, I took the column total for female and the row total for no, and that gives you female no. That's that number there, and down here in the expected. And this is actually how discrepancies are calculated with observed minus expected squared over expected. And so these are the numbers. So the bigger the difference between the observed and the expected, the bigger the discrepancy. It's a key topic right there, that if these numbers differ than what we expect them to be, then we have a bigger discrepancy. That's the point of a discrepancy. And these are some pretty big differences. You can see here it's about 20 each time. So if you square 20 and divide it by something, 20 squared is 400. So it's pretty big. And that does it. That is all the output we have, and we've analyzed it. I can't say this enough. Just keep analyzing these, be able to walk through every number and know what every single number means in these outputs.